Yeah. And Matt, notice, if you, those of you paying attention will notice there's a different surname on the board. Same person. I just changed my name since somebody in the abstract. But yeah, still me and Tobias. We're from different organizations, but working on similar stuff. So we thought we'd give it all together. We'll introduce ourselves a little bit more later, but first of all, I wanted to talk about the problem, why we're here. Well, that's nice. That works first time. It doesn't always. So first, we'll talk a little bit about why we're here, what the problem is, what we're trying to solve, what we're talking about, how we ended up working on it, and in particular, how we ended up working on it together, despite being, in different institutions. I'll talk about my part of the bit of the problems that I've worked on from UKCEH, and then Tobias will do similar from NOC. And then we compiled a slide of useful resources, links, tips, hints, other things we've learned on the way at the end. So this is the problem or the reason we're giving this talk and where we're coming from. At our institutions, there and in environmental science and wider, so hydrology, meteorology, climate science, oceanography, data's getting bigger. I mean, that's the simple thing. Particularly, large gridded data sets now, and model data sets and remote sensing data sets, so information from satellites. We've seen huge expansion in the amount of data we have in the size of data sets and the number of files, which is really challenging the way challenging the way the workflows and the way science has been typically done in the past in these organizations, where we download a copy of the data in our own little folder space, try and do a little bit of an analysis on it that we need to do with the resources local to us, our laptops, for example. So we're basically trying to find a better way of doing this, because we're now running into lots of problems where we haven't got enough disk space, the computational resources are a problem. We're proliferating lots of 10 copies of very large data sets all over the place. And on the right is some classic examples of data sets that are familiar to our field. I mean, don't worry about what the acronyms mean, but they're essentially very sort of common data sets that we're working with in fields of hydrology and climate science and oceanography. And top one was one that I just started, that was around when I started working in this area, and it got replaced by the one underneath, about 24 times the size, and you get the idea. And I probably don't need to hammer the point home too much. So ultimately, we're trying to improve the way, or make small improvements to the way scientists are able to work with these very large data volumes. You're going first. I'll let you introduce yourself.
Hello, everyone. My name is Tobias. I'm a research software engineer at National Oceanographic Center. I just put a picture here of my previous life. I used to be like a manager of a grill pro in Brazil, so that's look like my previous life. But now I'm a software engineer. So
cool.
For curiosity.
Does work. I'm not sure I like that picture anymore, but anyway, it's the nearest closest one I could find. I'm Matt, and my background is meteorology. So I had an interest in weather and climate and how the weather works. That led me on to doing a meteorology degree, and getting familiar with and interested in the very large numerical weather prediction models and climate models that are in that field and how they work. And then eventually that led me to where I am now, to being interested in that in general, but not just applied to meteorology. And these are sort of the projects that we should give a shout out to, I guess. So I'm working a lot on a project with flood and droughts research and infrastructure. I often get the acronym wrong, because DRI is used for other things. Part of which is trying to develop digital infrastructure to improve hydrological research. I don't know much about Atlantis. Remind me.
Yes, Atlantis is a project funded by Warwick.
Okay. Yeah. Cool. It's in a similar area. These are the sort of things that they've narrowed down the problem to. Ultimately, you've got these very large data sets. We know that they work quite well, that a potential solution to the problem of do all the analysis locally, is to make use of the cloud and formats that are designed for that, and workflows that work with that and that avoid having lots of different copies of data sets, and so you just access them in the cloud and don't download them. Sounds good in principle, but there's a lot of things we found that need considering, given this is quite new technology, quite a new idea, a new way of doing things. So the starting point is the common data formats that we're used to in working with gridded data sets is arguably not suited for this kind of workflow. It's not suited for access over laggy, high latency cloud internet connections rather than local disks. The way you structured the data set, so the rechunking bit, is highly important to how performant your access and analysis of the data is once you've got it up there in the cloud. And then once it's up there, you want to make the access to it as easy as possible and not have to introduce lots and lots of different, or introduce a whole new way of working for scientists who want to work with the data. And then a lot of scientists often want to have a quick visualization of what the data looks like at a particular time point or in a particular point of space, and that's turns out to be another problem that needs to be considered to get to work well. So first I'll talk a little bit about the whole idea of getting it in the right format. There are lots of ways of doing this, and lots of sort of cutting edge research has been done, and to the point that I wrote 3 slides on this last week, and then earlier in the conference I will just go with a new way of doing it that may invalidate one of them. But that's the way it goes. Like it's changing, and I kind of like that in a way. So we've got it's a big computational number crunching problem. You've got data in a particular format, you need to get it into another one, and these data sets are very big. So we've developed, a lot of people, particularly in the Pangeo community, which I always sort of struggle to describe exactly what that is, but I won't do it, so I won't do it. Have come up with, or tried to come up with, a framework that makes this a lot easier by trying to extract away a lot of the computational complexity of doing this conversion by building something on top of the compute engine or manager, which is Apache Beam. That has come with its own problems, so it's great that it can sort of, the idea is that it's on you have it running on a particular platform, or and then that it figures out how best to parallelize your computation and to give an architecture you've given it. However, it's like that's not a trivial problem. It's not a trivial bit of software to deploy and set up, which are maybe not great for trying to make this process as simple as possible. And even though, and any other point of the fact that this area moves fast is that although this, in theory, once you've got everything set up, is nice and easy for applying to different data sets very easily. You write one pipeline that says, I want, this is basically what I want to output, and the software can figure out the rest. There are now simpler ways of doing things that I think are a little more complicated to understand, but don't run into but haven't got the problem that you've got essentially quite a large software stack to maintain and deploy and keep working on. So the simpler way that I've found to do this is ultimately it's at a slightly lower level, so you are having to deal with a little bit more of the complexity of reading in a format and writing it out, and handling that yourself in your own scripting in your code. But there are ways of making it simpler. And again, it's a Pangeo thing that was developed to help with this, but is a little bit more bespoke. It doesn't quite have the applicability that the previous method I've tried using has. It's just very helpfully named a rechunker tool. It's not particularly glamorous, but it does allow conversions of the format conversions with bounded memory, which is a very useful thing. And it's not one that any of the other methods I come across can do. It's very useful. It's a bit more complicated to set up. And you do kind of need to, and it uses Dask under the hood, which is a good and a bad thing. Dask has got a lot better lately, but when we were first doing this, it was running into all sorts of problems as well. Or how about, rather than having to convert the format into something that's workable on the cloud, we skip that altogether. So there are ways now that can be done by essentially, I'm trying to explain this, but I'm still not sure I've got my head around it. But it basically creates a file format that is nice that works well with object storage and cloud data storage solutions. But instead of having the actual data in that format, the data sits underneath it, and you have your nice cloud compatible format that whenever it's accessed, or whenever bits of it are accessed, it basically byte maps to where the actual data is underneath. So that existing cloud software can work well with the format, it recognizes it, but under the hood, it just points to where the actual data is. And you get some performance cost with this, but not as much as you would expect. So that's something I discovered recently, which I quite like. A fun point is I was told how to pronounce the software on the right. So the format is no, I didn't actually mention that actually. The format that we tend to work with is called ZAR. And apparently I was told to pronounce this, that it's virtualizer, but more pirate. So I'll let people figure that out themselves. I've sort of touched upon it recently in the previous section that, okay, you've got to convert it into this new format, but this format is inherently chunks format in that each chunk is an object that the object store works with. That's how it works. And how you decide to split your data set up into different chunks very much impacts how performant your analysis is going to be. And I won't go into all the detail, but we did do a fun experiment on this. We actually do some science rather than just some infrastructure and software stuff, where we basically took one data set, tried a lot of different ways of chunking it. So did we chunk it purely in the time dimension, or did we do it in space, or did we do it in both? And then ran each of those scenarios through a different analysis. So the idea being, one analysis was very much, we're trying to pull out one time point from the data set and analyze it, and the other one being we want to pull out one entire spatial dimension for one particular time point. And you can sort of intuitively feel that if your data set, so let's do the one right at the top of the diagram on the right, where the data set is basically chunked 10 by 10 in space, but each chunk has the entire time series in it, or the data set in it. If you want to pull out one time step and just look at all the spatial points, to get that, you have to download every single chunk of the entire data set, because each chunk for that contains a little bit of spatial data you want also contains all the other time steps that you're not going to need to use. So that's the idea behind this, and therefore that comes with a huge cost in terms of performance, because you're moving around data that you don't need. The conclusion that we came to is that if you don't know exactly what type of analysis you're going to be using, or what the main use case for the data is, if it's going to be quite broad, then you kind of end up with a solution that is not great but not terrible for both types of analysis. That's the one that's sort of just to the left, the one I was just talking about, where the three polygons, I guess, kind of meet. And I'm running out of time already. That happens. So those are two problems to solve. Another one is, okay, now we've got some nice data that we've converted, ready for use. How do we make this as easy to use as possible? Because change is difficult. So if we can make this as easy and adaptable as possible, we can improve the science without having scientists to do too much work, I guess. The idea, again, there's quite a lot of work that's gone into this behind the scenes. This is very much not just me and Tobias doing this. Loads of other people in the community have worked on this. I've now got to sort of, at least for Python, I can only speak for Python at the moment, I've got it down to basically 3 lines of Python. It's a bit of boilerplate code you can stick at the top of your existing analysis code, and it will more or less act as if you're reading the data from disk. And again, the cost of these things is simplicity comes with the cost of a bit of performance. So there are more complicated ways of doing it that get you slightly better performance, but as a sort of introduction to, hey, yes, we're trying to move people to this new way of working. Yeah, don't worry, it's not too much of an issue. All you need to do is you can just talk people through a few lines of code that they don't need to worry about, and they can on their way. And then then the data gets loaded in. So I've just read in a 1.5 terabyte data set, although it hasn't actually, of course, read it in because lazy loading is a wonderful thing. You just see the metadata, but it's there ready to be worked with. And there is one more slide I was going to talk through, but you can ask me about it at the end. And that is, there's some. It's not quite as simple as I made it out to be. It never is. So there are some issues that come with just imagining your data is on a local disk or on a disk nearby, as instead of actually coming from the cloud, especially when DAS gets involved, which it does. But I can talk about that maybe in a question at the end if people are interested. I'll let Tobias talk through some of the visualization stuff. There you go.
Thank you very much. So during the last 10 minutes, Matt explained to us how ZAR and this type of cloud native formats are great for scalable storage analysis, but ZAR is still challenging if you want to do like browser visualization. So if you want to build a tool to show your data to other people or to build a full stack applications, because in the end, the users, they expect fast interactive tools, but WebGL and JavaScript still struggle with real-time decoding and subsetting of big geospatial data. And we'll talk about terabytes of size with several dimensions, time dimension, depth, latitude, and longitude. So JavaScript is still struggling on how to decode that. For many, many years, people are using some workarounds like GeoServer or NCWMS to serve the netdef files direct to the front-end applications. It works really, really well for a long time, but I don't think that now with petabytes of data that you put on object store, this is not a solution anymore. And another solution would be convert a ZAR file or netdef file to millions of cloud optimized TIFF and GeoTIFF files. This works as well, but it's really difficult to maintain. So I will show today 2 strategies that you can get your ZAR data, your big geospatial data in ZAR format, and show that in front-end applications. So the first approach will be using like a pure client-side approach. So in this case, I do not have any type of backend. I only have the object store and JS, HTML, and CSS files. And the second approach, I will show how you can have in a backend tile server that you read the ZAR data, get just the chunks that you need to show in the front end, create tiles and send the tiles to the front end application. I'll not spend time on this, but in the demo that I'll show in the end, if you want to try later, I also put the same data set using GeoServer and using Cloud Optimized GeoTIFF format, so you can do some comparison if you want later. So the data set that I'm going to work with is the NEMO near present day. NEMO near present day is an ocean model run by NOC. So it's 71 terabytes of size, if I'm not wrong. So it's a global ocean model that generates several ocean variables in 4 dimensions: latitude, longitude, time, and depth. It's not on regular grid, it's like a rotated pole. And the data is already on ZAR format. So it's already on ZAR format in object store. So I'm just using a small subset of this data set. So instead of 71 terabytes, I'm just using 10 to 50 gigabytes of size. It's not that much compared to 71 terabytes, but it's still a lot. If you want to think about showing that data in real time on front-end applications. So the first option that will show, the first strategy, the first approach, is showing like a client-side only approach. So in this case, I do not have any type of backend, just object store and your computer, your browser that's using JavaScript. So for this case, I'm using a library, an adapted version of a library called Carbon Plane Maps. So this library integrates together ZAR.js. ZAR.js is a JS library to read ZAR data, and DeckGL. DeckGL generates WebGL layers to add into maps. So this library integrates these 2 things together. So how's the workflow? ZAR.js opens metadata and reads the chunk based on the current viewport and zoom level. So if you are in the UK, it will just get the chunks related to UK in that zoom level. And then DeckGL will generate the WebGL layer for that part.
If you move your map, you zoom in and zoom out, it will get new data, Zarja to get new data and update the WebGL layer. So that's how it works. And in this case, the data stays in the browser. The second approach is using a backend tile server. So in this case, my approach is based mainly on modified version of titile. So in this case, backend interact with the object store, get the part of the file that it needs, and then generate the tiles on the file, on the fly. And because it uses Python as the backend with FastAPI, XArray, real-time, and raster, it supports various formats, projections, dynamic style, and processing. So you can get all the powerful of Python. So we don't need to be stuck with JavaScript. So in this case, in this approach, so the front end sends to the back end API endpoint request and pass information related to the position of the map, like Z, X, and Y. And then the backend XArray will open the data based on the query parameters, and real-time and raster will convert this data to a PNG image, and then the FastAPI will send back to the front end a response to the PNG image. So to increase the performance, we are deploying this at NOC using a Kubernetes cluster. We're deploying this on Jasmine, and because Jasmine does not have support for serverless application, we're using Knative that creates you can create serverless application in Kubernetes clusters. And I'm using also RAGs for caching to increase the performance as well. So this part is not mandatory, but it's interesting. Matt mentioned a lot about chunking and how chunking is important. Oh, 3 minutes. Okay, so that's why it's important, like, to do some transformation in the data. Like, if you want to reproject, it's a really good thing, because the data, if it's not a regular grid, reproject, it's a good way to make it a regular grid. Transform to create pyramids. I do not have time to explain what it is right now, but just to allow you to see the data overviews, and then rechunk it in a way that's good for visualization, okay? And then you send back again to object store. So this is the comparison that I did. I'm not going to detail, but my main choice, if you have any question, can ask me later. My main choice would be using Titanium, because it has full interactive, although it has a backend, it has full interactive, and you can add any type of data, JSON, shape files, and any other things. And it's not possible to do the same stuff with the client-side approach, okay? So I will show you now a live demo. Let's see if I have time for that. So this is the website. If you want to test later, you can try. So this is, I'm adding like the 20 gigabytes Zara data. So in this case, I'm using the poor client-side approach. You can see that the data is loading really fast. When I zoom in, you can see that the resolution of the image is getting better, because it's getting a better resolution of the pyramids. And then you can change that. If you change the time dimension, it changes the chunk size. We can also edit colors. So when you edit color, you are editing the CSS information on the layer. And this second approach here is using the backend tile server. So you can see that the layers, when I have the backend, the layers open like tiles. You can see if I zoom out, it's open, the tiles are bigger. And you can also change the zoom level, sorry, the timestamp, and change colors as well. And another thing about having a backend using XArray, that you can bring the data to the front end. So here, for example, I'm getting 2 data sets of currents, U and V components of currents, and I can create animations the front end in real time. So I'm loading 20 gigabytes of data, processing it, and create animation of currents. And I can even interact with the currents and change the timestamp of these big data sets. So final reflection. So I think I'll just go quick here. So this Zara is still the cutting edge technology. So it's a really new stuff. So there's a lot of new things happening, even from 2 weeks ago to today. A lot of things that has changed. So things breaks even more often. So it's hard to keep track of everything. So it's good to have other people from UKCEH to work together, to learn together. So it's good. It would be great to have other people from other institutions to learn with us, and we can exchange some experience. Yeah. So yeah, these are the resources that we are using here. So if you want, you can take a look into presentation later to take a look at what we're using, what is on our radar, and all the useful resource that you may want. So all the links, articles, papers, repos that we are mentioned here are available on this link. So yeah, thank you very much for your time. If you have any questions, please let us know.
Thank you very much. So we'll just switch over to get Slido up here so we can see questions, but we do have a few that have come in. The first one then we'll ask you is, how is the data stored during acquisition, and could we have used this ideal chunk to avoid the rechunking later on?
Ideally, yes. The problem being that the sources that is often, ideally, yes. A lot of this data is coming from models themselves, which are being run and outputting, and simply chunking them. The NetCDF is a common one. Chunking that in the right way is something that is just not on people's radars, really. It's just, oh, it's NetCDF, whatever, I don't need to worry about it any more than that. Arguably, that is something that, would be nice to change, so that it would be automatically in a nice chunking format that we don't need to really worry about conversion and rechunking and all this complicated stuff. But it's simply, the problem is that that's only one format as well. There are other formats that the data comes in, which it's not chunked and it has to be. So yeah, in an ideal world, we wouldn't have to do any of that stuff, but really it's too messy and not on people's radars to do the formats that support chunking, the ability to do that and doing it in a nice way is not really on people's radars at the moment.
And I think the ideal chunk is very difficult because it depends on because for front-end applications, the ideal chunk is one way, but if you want to do for analysis, completely different chunkings.
Thank you, and we have time for one or two more maybe. So have you looked at using the intake library for access via catalogs?
Yes, I didn't mention it just because of time. That is one of the ways I looked into to try and making the access as easy as possible. I sort of skipped over some detail in my, let's do it in 3 lines of Python approach. Intake has some, like order methods, intake has some pros and cons. I remember that actually generating the intake catalog file was a hurdle that I found quite annoying. And a lot of at the moment, it basically we're at the stage of where we don't have enough data to need to catalog it to do that. We can provide people with a URL on an existing catalog service that the institution runs, for example. The data has to see the catalog, see the data center. Actually, that's not one. That's the wrong one. But yeah, UKCEH runs its own data catalog for which we can link to basically an environment in which you have these 3 lines of Python and the link that you need to use to access the data. Found that was a slightly simpler approach than going down the intake or stack route, but they're both still very much on my radar, I think.
At NOC, I think we use much more stack.
Yeah.
Because I think intake is good for any type of our data, but I think if you want to work with big geodata, I think stack is much better because we can put all the metadata together. We have a lot of built-in tools that you can work in JavaScript and Python. So intake is simpler, but I think stack is more robust for a long period of time.